So we are on section 1.6, transformed sine and cosine functions. So we are talking about graphing we said the basic function is either sine and cosine. We take this thing and move it around in all sorts of ways. We have half a dozen ways of kind of modifying the picture. These are captured in formulas such as this one. So we have some a times sine of, say, b times x minus c plus d. Last time we went through quite a few examples where one of these four quantities were something other than what is in this basic case, and we showed one by one what do they do to the picture. The question is now a little bit more complicated. What if we have all of them or some of them present in one problem? What happens in when you are changing many things? Okay, let me quickly go through the run of these things. We said A is the amplitude. Amplitude for any of these sinusoidal functions is the measure of how far above or below the midline you go. So maybe better go ahead and draw this midline first. So this is the midline. D, for a basic function, midline is just the x-axis. If you take it, move it up or down, you do it by adding or subtracting a quantity here, and that's the location of the midline. So midline itself has an equation, y equal to d, that's your midline. The amplitude is how far above or below the midline you go. So this is the amplitude. So the amplitude A, let me change the coloring here so things stand apart. So that is our amplitude A. That's also going down here is amplitude A. In case A is negative, you're actually doing two things. One is stretching or shrinking the shape, and negative means you're flipping it across the midline. So keep that in mind. There are two effects. Next item is the phase shift. So we have the quantity C over B is indicated as the phase shift. That's the amount by which the graph has moved to the right or left corresponding to in relationship to the original picture. And we have another concept here, which is the concept of period. This original sine function, you remember, sine function repeats itself every 360 degrees. So from 0 here to 360, the picture repeats. Or from 0 to 2 pi, the picture repeats itself. Now if I take my variable x and multiply it by something, like if I double x, it means everything runs twice as fast. I've just changed the x same amount as before, but because of a factor of 2 here, everything's going to run twice as fast. Running it twice as fast means this picture is going to shrink by a factor of 2. So if you want to use radians for a basic function, the period would have been 2 pi, but if you have a 2 here, it will become 2 pi divided by 2. If you have a 3 here, the period becomes 2 pi divided by 3. So this factor of b here indicates what your period going to be. So period will be the number of cycles you are going to have in span of 2 pi radians, or in a span of 360 degrees. Higher b's means you have more oscillations in the same space. Low b's means you are going to require more space to go through same number of oscillations. So we have 4 quantities to think about. We have these two and also these two. The effect of these two is to modify the shape horizontally. Like phase shift simply means moving the picture to the right or to the left. Modifying the period means you are shrinking or stretching this thing horizontally. So these are horizontal modifications. These are more vertical modifications. When you are touching the amplitude, you are making the picture taller or shorter. When you are modifying D, it means you are taking your picture, original picture, moving it up or down by a certain amount. So 4 effects showing up in this style. Now, the amount of phase shift in this style might look a little bit strange to you, and for that reason, sometimes these texts write the formula in this style. So when you want to compare or give an answer with respect to what is a phase shift, remember to factor this factor of b. Whatever is left is inside another parentheses. Now phase shift shows its head here, and then you put your midline at the end. So phase shift is going to be obtained by factoring your b. Whatever is left here, negative of it, is going to be your phase shift. Okay, so again, you are factoring your constant b. Whatever is left inside of a parentheses, whatever number you have here, negative of that is called the phase shift. Now, these are rather large number of details to digest all at the same time, and best thing to do is to practice. So let's take this example again. We had what? 1/2 of sine of x plus pi over 2. What we realize is that certain quantities kind of perhaps hiding from our view, but let's make them explicit. Our d here is what? Our d is 0. I am not adding or subtracting anything. It means I have not changed the midline of my function. We are still operating around the x-axis. Who's my b? Sometimes the students fail to see a number that is not explicitly written. b is multiplier of x. What's my multiplier? Well, it must have been a 1. 1x is same as just x. So that's why we don't write the 1. Okay, we make a comparison against the formalism that we have up here. This is my d is 0, so I haven't moved up or down. My amplitude is 1/2, which means I have taken my wave, instead of having amplitude of 1 that is, in this case, I'm cutting it to 1/2. So far, the fact that this is a 1/2, it tells me that if my original function looked like this, if that was sine of x, after I multiply it by 1/2, it looks like something kind of shorter. So this is 1/2 sine of x. So I'm done with these vertical translations. We were lucky that one of them wasn't there for us to worry about. Now we come to the horizontal modification. Horizontal modification, again, we get lucky that b is just 1, so we don't have to worry about anything. So if you want to factor, it is already factored. My b is already factored. Now I said the negative of this quantity, it becomes my phase shift. So what is my phase shift here? Okay, so minus c over b is supposed to be plus pi over 2. So c over b itself had to be what? Minus pi over 2. Okay, so we are going to move left. So when this quantity negative, it means we are going to drag our picture to the left. If I had here, for example, minus pi over 2, I would have gone to the right by that amount. Let's do several examples, we'll see. So negative of this quantity is going to be our phase shift. By the way, period, before we mention anything, we just said that we are not touching the period. Period is the same as before. So period, which was 2 pi over b, is still, due to the fact that b is equal to 1, period is still 2 pi. So I'm not shrinking it or stretching it or touching anything. It's just staying put. Next, we are going to have our phase shift. Our phase shift is going to move everything by this amount horizontally. Negative value for it means back up. Positive value in this formalism. Positive value would have shifted us to the right. So what we have here, we start from here. That is, I take this point, move it to the left. You could have taken this high point, move it to the left. You could have taken this crossing, move it to the left. Any one of them would do. So I'll have this one. This low point now comes here. This crossing goes over there. So one cycle of now, once again, it takes a while to get comfortable with these 4 items, remembering the order in which to do them and all of that. It can be a bit intimidating. What's an alternate way of getting the picture? Making sure that you have the correct picture and then double checking yourself. Well, that is going to be point plotting. Point plotting, kind of a primitive way of doing things, but things are kind of robust. It's hard to go wrong in that. To do point plotting, you need to familiarize yourself with the original picture. So that one you need to know very well. Well, we know that one hopefully very well. Sine of x is characterized by these 5 points. So why I need to know the basics of my grandfather shape. Okay, sine of x looks like this. It has 5 important points on it. What are these? 0, pi over 2, pi, 3 pi over 2, and 2 pi. Or if you are dealing with degrees, exact same set of location, 0, 90, 180, 270, 360. What happens at any of these things? Well, I know at pi over 2 I have my 1. At 3 pi over 2 I have my minus 1. At the other 3 points I have my zeros. Okay, how is that going to help me with respect to my function here? I make a table. I ask myself, when is it that the input of this function matches the input of my model function? Here's my model or original function or the grandfather function, however you want to call it. I ask myself, when is it the argument of this thing matches the argument of that one? That is, I'm going to track each of these 5 important points. I want to know, where does this point go? This point happened when the argument of this function was 0. I ask myself, when is it that this guy becomes 0? X plus pi over 2 equal to 0. Well, when is that? For what value of x? I mean, what's the solution of that equation? X is equal to minus pi over 2. What does that tell me? It means this point went here. The advantage of this tracking, so point plotting is a kind of, let's give it a more respectable name, so you can also call it tracking. There's some meaning attached to it. This point comes here. Meaning, if I take x equal to minus pi over 2, plug it in this function. So minus pi over 2 plus pi over 2 is 0. Sine of 0, I hopefully remember that. Sine of 0 is 0. Multiplied by half, it is still 0. Add a 0 to it, it's still 0. So this point has moved on here. Next, I say when is the input matches the input at the high point. So I say x plus pi over 2 equals to, here is that event at pi over 2. For what x is it that x plus pi over 2 is equal to pi over 2? Let me rewrite this thing. So what's the solution of this equation? X plus pi over 2 is equal to pi over 2. X is equal to 0. What does that mean? It means this point came here. Well, let's go check it out. Pi over 2, when x is 0, I put x equal to 0 here. I get sine of 0 plus pi over 2. That is sine of pi over 2. Well, sine of pi over 2 is 1. Here I'm multiplying it by half and add nothing else to it. So I have come to a half. So here we record our y values. Our y values first was 0, then we came to a half. Now, let's see, when do we track this point? So, okay, x plus pi over 2. X plus pi over 2 is my input. When is it that my input matches this? When it matches that, it means I have arrived at that kind of an event. I say, when is that? That is pi. So again, we are tracking these 5 points. X plus pi over 2 is equal to pi. Now solve that equation for me and tell me what is x. X plus pi over 2 is equal to pi. So what is x equal to? Pi over 2. Very good. What that means is that this point has come to here. So this was minus pi over 2. This was tracking of that. 0. Now at pi over 2. Now let's talk it out. When x is equal to pi over 2, this is pi over 2 plus pi over 2 is pi, as we expected it. Sine of pi is 0. 0 times a half is still 0. Plus 0 is still 0. So I'm stuck at 0. All that means is that that point got tracked to here. We have gone 3, 2 more to go. 3 pi over 2 and 2 pi. So next question. I take the input of, let me write my function here again. I'm trying to draw 1/2 of sine of x plus pi over 2 and then nothing here. Input here x plus pi over 2. I ask, when is that input equal to 3 pi over 2? By now you have learned the trick. Just subtract pi over 2 from, so we get a pi. At pi, what's going to happen? We expect the duplication of this event, which at 3 pi over 2, this was negative 1. Let's try it again. If when x is equal to pi, pi plus pi over 2 is 3 pi over 2. Sine of 3 pi over 2, that's what you see here, is minus 1. You multiply by half. It's minus 1 over 2 plus a 0 is still minus 1 over 2. So at the location 3 pi over 2, our height becomes, here was a half, here is going to become minus a half. So this was 0 here. Last item, when are we gonna hit that 2 pi event? When my input becomes 2 pi. So I say, well, when does that happen? X plus pi over 2 is equal to 2 pi. I subtract pi over 2 from here. That is going to give me 3 pi over 2. Here we got minus a half. 3 pi over 2, I plug it here. It becomes 2 pi. Sine of 2 pi is 0. This thing just boils down to 0. So I arrived at this location. Now I connect my points and make sure it becomes a smooth curve. So I have started at 0, went to a half, came down. That's the graph of this function. So we did tracking. This one got tracked to this location. This one got tracked to this location. This one came here. This one came here. And this one came here. It doesn't have all of this flavor to it. Oh, well, what are we doing? What's happening? This is giving more of like skeleton of the whole event, giving more description of what's going on here. Here we are kind of following our nose to see what's going to happen to each of these individual points. Track them. We know that the new shape is like this, but we kind of queasy about it. Well, what happened exactly? What's going on here? Those 4 ideas really capture what happens when you are solving this equation repeatedly. It's just capturing all of those things in one place. Now let's go ahead and do a few more examples. It really requires a lot of problem solving for the whole thing to add up. So what you want to do is to read section 84, page 84. That gives you a lengthy set of rules to follow to see what's the effect of A, B, C, D, in which order to follow each of these modifications to get your final picture. So that was problem. So you go ahead and read that table. I don't repeat it here. We have been doing it in the context of the lecture. That was problem 11. Next question. Or maybe I take some of the easy ones and then try to build up to some of the Monday. Okay, let's go ahead and pick some other examples here. Yes. No, well, you need to know those things, but we are concentrating on the stuff since the first test. So the stuff from the first, the focus is not going to be on those things, but of course you still need to know what's a sine and what's a cosine. So the questions are going to resemble what we are just doing right now. Another relatively simple question. The ones that just modify a couple of these factors are easier. The ones that modify all 4 of them, and perhaps some of them are negative, becomes more complicated. So problem 13 is going to be 3 cosine of x minus pi. Let's do it in the style that we have been talking about. Several styles are available. As usual with trigonometry, same kind of idea shows up in so many different forms. You want to become comfortable with all of them. Okay, what are the factors here that are modified? First of all, what is the basic function? Basic function is cosine of x. When everything is being modified, you have to be ready for the following. Cosine of some multiple of x minus some quantity plus some number. Just as before, these four items represent exactly the same thing that we had before. For dealing with the phase shift, one way to handle it is by this factorization, so that the phase shift shows up after you factor your b. Now let's go ahead and compare. This is not a very complicated problem because not everything has been changed. What is our d? D is 0. So that means we haven't shifted the function. Which direction haven't we moved it? We haven't moved it up or down. So midline of our function is same as before. By the way, we need to know what the cosine is. We don't want to struggle on that when we are answering questions of this style. We need to have that by memory. So cosine, we remember that starts at 1, pi over 2. So it has some appearance like this for the first fundamental cycle of it. Okay, what is it that is changing? What does this 3 do to it? Which one of those quantities is 3? Is A. So what do we have? Let me draw it all at the same time. So our basic function perhaps was this. When you say amplitude is 3, every height is become triple of whatever it was. So 1 becomes 3, 0 stays as 0, minus 1 becomes minus 3, 0 stays as 0, 1 becomes 3. So if I had 3 cosine of x, the same picture would have been looking like this. So far we have 3 cosine of x. Our phase shift. Fortunately, b is 1, so I'm not touching the period. I'm not squeezing this thing or stretching it in a horizontal direction. Its period is still 2 pi. So 2 pi divided by 1, here is our b. b is 1, so we have nothing to worry about there. Last item is our phase shift. Our phase shift is c over b, negative of this quantity, indicates the amount by which we translate horizontally. So what is our phase shift? So negative of this quantity will be pi divided by 1, it just becomes pi. Which way do we go? To the right or to the left? So let's show this thing in green. Moving by pi in the direction that you see here, like if it is positive, we are moving right, negative, we're moving left. The item we talked about last time is already factored in with the negative sign here. So pi indicates that each of these points is going to move over by pi. This one is going to come here. This crossing is going to So far what have we done? We have taken this point, moved it by pi over there. We take this point, move it by pi over there. We take this point, move it by pi over here. Moving, let's see. That crossing comes here, and then finally this point moves by pi over here. So this becomes the graph of 3 cosine of x minus pi. Of course, we could take this tile and copy it over on the right and left. So if you want to continue, the graph of course exists all over the place. It's not disappearing from the other locations. Okay, this was one style of answering this question, just to refresh your memory about those reflection identities we talked about last time. You can do it completely different style than anything we have talked about, just as a matter of practice from section 1.5. Let me see if you remember. Can you simplify? Yes. Cosine of x minus pi, the original problem. So this green one is our green function here. What I'm trying to arrive at the next one is that what do you think is the relationship between this green one and this blue one? Let me draw some more of the blue. They are what? Which mathematically you do what? What do you do to the equation to, you notice it's flipped upside down, is that right? Is that what you're saying? The green and the blue looks to be pretty much the same, except that this is up here, this is down here, or vice versa. So what do you think? Yeah, if you were to come up with a formula for this green curve here, what would you write? If that's all you wanted to do, you had an alternate style of doing it, which would be what you would write. If you have this blue one is 3 cosine. You want to flip it upside down. What do? What's a simple way of flipping something upside down? No. If you have 2, reciprocal of that is 1/2. This is not below the x-axis. They are both above the x-axis. They are reciprocals of each other. If I want to have a point up here, I want to have another point down here. If this is at 2, where is this one at? -2. So if this is at 3 cosine x, I want to make it come down here. What should I do? -3 cosine x. So still another alternate style. We have so many ways of arriving at the same answer. -3 cosine of x would have done the same thing. Now this is a practice from section 1.5. Simplify cosine of x minus pi. What did we deal with in that section? In that section we talked about reflection identities. Let me, instead of x, use theta so we don't get confused over axis or anything. Doesn't make any difference. What was the deal over there? If I have this angle theta here, and I've chosen point on the ray that comes out of this location, let's label it as A and B. Suppose I want to subtract pi from this. Which way do I go? How do I turn around to arrive at an angle, which is theta minus pi? Think about angles as rotation. Like here you rotated by theta. You want to rotate by minus pi. Which way do I rotate? Do I go counterclockwise or do I go clockwise? Clockwise. Here is my pi. Tell me when to stop. Press the buzzer when you have to stop. Very good. So here is This angle is theta minus pi. Theta, this direction, minus pi, this direction, that brings us here. So if that location was AB, what are the coordinates of this point? Okay, distances from the origin are the same. Now, cosine of an angle was a ratio of two quantities. What were those quantities? Like if you have, if you want to talk about cosine of theta, you would have talked about the ratio adjacent to hypotenuse. Instead of adjacent and hypotenuse, we use the coordinates. What is the adjacent here? A over R. Now, for cosine of theta minus pi, what is the adjacent of that one? Yes, it's going to be cosine of theta minus pi would have been minus A over R, which is just minus of cosine of theta itself. What does that mean? Well, we practice this identity from that section again. Cosine of theta minus pi is minus cosine of theta. So if your question was graph 3 cosine of x minus pi, if you had remembered that identity, say, let me make my life easy. This is simply minus 3 cosine of x. So what do? I graph my cosine. Here's my cosine. I take it, stretch it by a factor of 3, and what else should I do? How do I affect this negative? Flip it upside down. So here is minus 3 cosine of x. So what in order? The blue one was just the original cosine of x. The green one is what you got by tripling it. The black one, the final answer, is you make it negative by flipping it upside down, and that brings it back to the final answer, y is equal to minus 3 cosine. So next time we are going to solve more problems from section 1.6. Try to finish these problems. It is going to take quite a bit of time to get used to this thing. And we'll talk about it more on Monday and have a quiz on Wednesday.